You can also set up a vector data type, which is sort of a very, if you just wanted to find that central region and not the blanks in the front and the back, then you would set up blocks. In this case, you'd set up 6 blocks. Each block has 6 elements in it, and each one has a stride. So they're 18 elements apart. That includes the elements of the block. So it's that 12 plus 6. So it's the difference between the fronts of each of the blocks. So if you use such derived data types, what you're saying is that for this section of the file, so the extent of this file type is 96 elements. It can be 96 doubles. Is that I can only access data that's in those red spots. So those 6 elements, whether they be doubles or integers. So this is a syntax for creating the derived data types. And I've pretty much discussed all the elements that go into the call. For instance, in the subarray, you need the number of dimensions. So you can use it on 2D arrays, 3D, 4D. It's abstracted to whatever you want. You need this array of sizes for the global array, the subsizes for my individual process, what portion of the array do I have, where that starts, and everything else. You generally have to commit those with MPI commit, MPI type commit in order to use the data type. Now, with MPIO, there's several options you have for writing and reading data. So, for instance, this pictorial, let's say this is a file, and I want to read or write the elements that are in the red blocks. So I want to skip 108, say doubles, and I want to write 6 doubles. And I want to skip the next 12 and I run and write 6. So this is sort of strided. Now, you can do an explicit read-write where you can actually set your view, but not limit it to anything. So just view everything and start 108 into the file. So you want to start at the first set where you want to read or write data. You can write, I'll just use write in this case, you can write the 6 elements. And then you can seek 12 more elements and write the next 6 and seek and write. So that's fairly manual. You can actually use derived data types where in the same file you can create a derived data type for that central portion which defines the blanks and the elements you want to read and write. So what that buys you is you've passed information to MPIO about where my blanks are and where my data actually resides. So in order to read those 6 blocks of 6 elements, so there's 36 elements total, you can actually just use the derived data type and write or read 36 elements. And let the derived data type and the file view describe where those elements are coming from in the file. So the only other thing you can do with MPIO is you can use collective I/O. So most of those calls I showed you before are actually independent I/O, where each process can independently access the file, read and write its data, and come out. With collective I/O, the number of processes that are sharing the file can actually collectively enter the file and then use a shared file pointer to collectively gain information. So let's say we had a file on a disk and we have several processes trying to access information in a file. They can do this at different times, so the disk might have to jump from the back of the file to the front of the file as these processes in not synchronous order try to access data. So with collective I/O, you can sort of aggregate all these processes together and try to sequentially access the file that direction, and that can improve performance also. By the fact that the calls are collective, each of the processes can share information about what portions of the file do I need versus what portions of the file do you need or other processes need, so they can try to coordinate a little bit better about how I/O is performed instead of almost doing random I/O on the disk. So this is the read and write syntax. I won't go into a lot of detail about it. You give it a file, you give it an offset, you tell it how. It's like an MPI send and receive almost, where you actually tell it a buffer and how many elements to read or write. And also at the end, you close files and you free data types, so I won't go into too much detail about that. So MPIO hints, you can actually, either in the application or external to it, you can define these MPIO hints, which gives additional information to the MPIO library. These are generally implementation specific, so on the Cray XT5, here's a list of some of them. This isn't all of them, but these are the ones I find the most useful. So with MPIO, it can actually directly interact with the Lustre file system, so you can define in these hints what my striping factor is, which is actually the stripe count, or the stripe size, which is the striping unit. MPIO can use this if you're using collective I/O in order to stripe align I/O for you. So one thing I probably didn't mention before is that you get a very large boost in performance if you minimize the contention that each process has for an OST. So if you stripe align the I/O, you get an increased performance. So if you give MPIO information about what your stripes look like, how many disks you're using, and what the size of your stripe is, it can help stripe align your I/O for you. So you can actually set collective buffering and data sieving. So in collective I/O, I'll go into a little bit more detail about this in the next slide, but what you can do, if doing collective I/O, I'll show you on the next slide. So as far as collective buffering and data sieving, so collective buffering, when you're doing a collective operation, can actually aggregate your I/O into a buffer. So the point of this is that say you had a set of processes that was doing I/O, fairly little amounts of I/O. They can be collected into a buffer, into one process. This also helps with the stripe aligning, because if MPIO knows about what the stripe size is, what the stripe count is, it can define a number of buffers equal to this number of your stripe count, and they can be stripe size, so that a buffer actually completely dumps into a stripe, so you help stripe align things. Data sieving tries to decrease the amount of sort of reads and writes you do. So in this particular example, sort of like the example I had before, say you were reading, but you wanted to read only those red blocks, so those sets of 6 elements. Well, instead of doing 6 different reads, with data sieving, you can actually read that whole contiguous chunk, blanks and all, and actually pull from the buffer the actual information you wanted instead of reading the file 6, 7, 20 times. So the summary on this particular section is that there are 3 levels of I/O possible. The performance generally increases as you go up, but it does kind of matter how well performing your I/O is in the first place. MPIO won't increase performance if it's designed well on the forefront. So if your I/O is already stripe aligned, if you're already matching your file system, then you probably won't get an increase in performance by having MPIO do that for you. But if you are not doing that, or if you're incapable of doing that, then MPIO can help improve performance by doing some of that for you. It won't do everything for you. And also you can give MPIO hints to help the perform your I/O a little better. So we'll talk about some common I/O considerations. So coming off of the general I/O discussion and the MPIO discussion, there are a couple things that people do inside applications that are good or bad. So I'll talk about standard input and output, buffered I/O, which I talked somewhat about previously, binary files and endianness, and also subsetting, which I talked about, I think, in another slide. So as far as standard input and output are concerned, a lot of people in applications will write their applications so that they output standard output or standard error messages. A lot of these can be debugging messages. So you can have messages like, you can say hello from every process you have. Of course, if you're running an application at 32,000, 50,000 cores, you have 50,000 standard output little messages say, hello, I'm process 50,000 or so. The thing to consider is that in most launchers, so MPI run, either MPI run, app run, IB run, the standard output and standard error streams are serialized into the launcher. So this is generally serial I/O. So you have 50,000 processes in which that I/O is written to your file in a serial fashion because it's aggregated. So whenever possible, you need to disable the debugging messages when you're running in production, or limit the amount of them that you actually use. So as far as buffered I/O is concerned, so this is like the spokesperson method where you have many processes communicating their data to a single process or to a single buffer, in which is written to disk. This does serialize your I/O, but it can help if each of the writes that each of the processes would do is small. So you can aggregate them into a single buffer and do one write instead of 20 small writes. The thing to remember about this is that frequent buffer flushes are harmful to performance. So if you don't let the buffer fill up, you can't get the maximum impact from it. This is a particular case study. So we've had an application which was writing a 1 gigabyte file, so not a very large file. But it was taking about 18 minutes to write this 1 gigabyte file. And the reason that it was taking so long is if you look at that table at the bottom there, so all the way at the last column, the average size. The average size of those writes was 512 bytes. And it's writing a lot of those. So it's doing that over 2 million times. So if you used a buffer, so in this case we used 4 64 megabyte buffers. So all that little I/O, all those 512 writes were being aggregated to a single buffer. And that buffer was actually flushed, I think, 17 times or so. Of course, now the average size is the size of the buffer, so it's 62 megabytes or 64 megabytes or so. Now that took 4.5 seconds instead of 18 minutes. So this is an extreme case, of course, but it does show where buffered I/O can help you. As far as binary files and endianness are concerned, so on Kraken, for instance, it's a little endian system, so it stores all of its data sort of in little endian binary format. So for a compatibility to other systems, which may be big endian, some people like to write their binary files in big endian on a little endian system. In order to do that, you have to swap the bytes in memory, so you have to swap it in memory before you write it, because the data is actually stored little endian in memory. So as this first example shows that what can happen is even in a large I/O write, if you're doing the byte conversion, well, you have to swap the bytes. So what size do you actually do that on? In this particular example, it's on 4K pages. So 4 kilobytes of data are being swapped at a time and then written. And then the next 4K are being sort of loaded up, swapped, and then written. Now, this impact is mitigated by the fact you have OS buffers. So you have some buffering going on which could collect all these 4K writes. So you don't see that much of an impact. But if you were to do anything that would bypass the OS buffers, or you institute some other form of buffering which doesn't do so well, you'll get a large hit in performance by doing this. Although you do see some hit in performance by doing the byte swaps anyway. And you can see at the bottom here is if you just write a little endian binary, well, the same I/O is, you only do 350 big writes instead of a huge amount of small writes. But I will say again, that is mitigated by the fact you do have OS buffers, which can make those perform similarly, except for you won't have the impact of doing the byte swaps. Real quick about subsetting I/O. This is the same as the combination technique I described earlier. So if you think about the limitations we talked about earlier, where, say, in a file per process, the major limitation is that you get bad scaling at large number of processes or large numbers of files. So if you were to subset your I/O so that only a certain portion of your processes were to write their files at any given time, you could help decrease the contention for file system resources. So instead of having all 50,000 processes write their files all at the same time, you can have a set of 512 or 1,024 write at one time, and then the next set of 1,000, then the next set of 1,000. The major limitations where you're using a single shared file, besides the Lustre limitation where you can only stripe it across 160 OSTs, so a single file can't utilize the whole file system. You can also do this in where you have multiple shared files in order to decrease that level of contention and to utilize the entire file system using multiple shared files. So at the end of this, I have sort of sets of further information. So I didn't go into complete detail on most things, but I have here online resources for talking about Lustre. I didn't talk about GPFS, but I have its reference here. HDF5, NetCDF, and also some further information on MPIO, collective buffering, data sieving, and various things and using derived data types in MPIO. So I'll be happy to answer any questions you might have concerning this talk, and I believe that's about it.